20,000 pounds of cast iron sliding across a 20-foot bed, cutting 1 inch of steel per pass while modern CNCs nibbled away at a hundredth. The machine shops called them dinosaurs, but the dinosaurs could do in 10 minutes what digital precision needed 2 hours to accomplish. So why did we make them extinct? 1954, Cincinnati, Ohio. The factory floor shuddered as the Cincinnati Shaper Company's Model 36 rolled off the assembly line, its 24-foot bed stretching like a steel highway, ram assembly weighing 7 tons alone. Foundry workers had poured 18,000 pounds of Meehanite iron 3 months earlier, letting it age in the Ohio weather while molecular stresses bled out of the crystalline structure. This wasn't a precision instrument. It was controlled violence. The Shaper's ram moved at 40 feet per minute on the cutting stroke, returning at 120. Each forward pass dragged a single-point tool through hardened steel with forces that would shatter lighter machines. The physics were brutal and simple. One cutting edge, powered by momentum and mass, removing metal the way glaciers carve valleys. No spindle run-out to worry about, no tool deflection from multiple cutting edges. Just one massive tool bit backed by tonnage that absorbed every shockwave from interrupted cuts. If you want to see more videos about old machines, make sure to subscribe so you never miss another video. Modern manufacturing engineers in 2025 would call this primitive. CNC machining centers promised precision measured in microns, 5-axis simultaneous contouring, tool libraries with hundreds of options. Silicon Valley mantras echoed through every technical conference. Faster spindle speeds, lighter structures, adaptive control algorithms that optimized every millisecond of cutting time. The message was clear. Mass was obsolete. Computation was king, and anything that moved in straight lines belonged in a museum. Yet in Norfolk Naval Shipyard, a 1947 Rockford Shaper still flattened 40-foot destroyer deck plates in single passes that would require a modern CNC mill to make 15 separate output cuts with tool changes between each one. At Timken's bearing plant in Canton, a 1962 Cincinnati planer-type Shaper machined hardened bearing races in operations that stumped younger engineers who had never seen such machines run. In locomotive rebuild shops from Altoona to Sacramento, Shapers handled work that CAD software couldn't even conceptualize because the geometries were too simple, too large, too heavy for the delicate world of high-speed machining. The contradiction lived in the iron itself. These machines existed before planned obsolescence, before proprietary software, before the assumption that industrial equipment had a 10-year life cycle. They were designed when American manufacturing still believed that a 20-ton machine tool represented a multi-generational investment, not a depreciating asset to be replaced when the control system became obsolete. The ram's dovetail ways were hand-scraped to precision, measured in 10,000ths across spans that would make a modern metrology engineer weep. Everything built to be rebuilt, restored, and returned to service by craftsmen who understood that geometry lived in the iron, not in the computer code. Tommy Vance ran his hand along the ram of the 1958 Skokie Shaper, feeling for the telltale warmth that meant the bearing oil was circulating properly. At 67, he was the only machinist left at Kearns Heavy Industries who remembered when 5 of these giants had filled the big machine hall. Now only this one remained, tucked in the corner like a relic that management couldn't quite justify scrapping. "Incoming job's a 6-foot press frame," his supervisor called across the shop floor. "Engineering says it'll take 3 days on the VF6 with a dozen tool changes." Tommy nodded and pulled up the blueprint on his phone. A heavy forging requiring 12 inches of material removal across a flat surface, interrupted by bolt holes and stress relief pockets. The young CNC programmer, Sarah Chen, appeared beside, him holding her laptop. "I can have the program ready by tomorrow. We'll use a 4-inch face mill, take 0.030 per pass. That's about 400 passes total with strategic toolpaths to manage the interrupted cuts." Her simulation showed the spindle darting back and forth like a hummingbird, avoiding the holes, calculating approach angles, backing out to clear chips. Tommy studied the forging, noting how the casting skin was still intact, hiding potential hard spots that could chip carbide inserts. "How many tools you planning to burn through those hard spots?" Sarah's simulation hadn't accounted for material inconsistency. The software assumed homogeneous properties that forgings never possessed. He walked to the shaper and opened the tool post. One tool bit, high-speed steel ground to a simple geometry that had remained unchanged since World War II. He could reshape it on the bench grinder in 2 minutes if it dulled. The carbide inserts Sarah's program required cost $45 each, and interrupted cuts in variable hardness material would destroy them unpredictably. "Watch this," Tommy said, mounting the forging on the shaper's table. The setup took 15 minutes. No elaborate fixturing, no precision vise alignment, just clamps and blocking that positioned the work surface perpendicular to the ram's travel. He set the stroke length to clear the part by 6 inches on each end, adjusted the cutting depth to 0.100 inches per pass, and engaged the feed. The ram accelerated forward, 7 tons of cast iron carrying a single tool bit into the forging with force that made the concrete floor transmit vibrations through shoe leather. Metal peeled away in a continuous ribbon, curling off the tool in a silver spiral that piled beside the machine. Hard spots that would have shattered carbide merely dulled the tool's edge, which Tommy touched up without stopping the machine. 40 minutes later, 12 inches of material had been removed in 120 passes, each one taking metal that would have required Sarah's CNC to make multiple careful approaches. The mathematics of metal removal had remained constant since Joseph Whitworth built the first precision planers in 1842. Force equals mass times acceleration, and shapers multiplied both variables to magnitudes that modern machine tools deliberately avoided. The ram assembly on Tommy's Skokie weighed 7,200 pounds. Driven by a 15-horsepower motor through mechanical advantage that converted rotational speed into linear momentum, it carried the cutting tool forward with energy measured in foot-pounds that dwarfed the cutting forces of contemporary equipment. A modern CNC machining center might apply 500 pounds of cutting force through a rotating tool at 2,000 RPM. The shaper applied 3,000 pounds through a single point traveling at 40 feet per minute. The difference manifested in how material yielded to the cutting edge. The CNC's approach relied on speed and multiple passes to prevent tool deflection and thermal damage. The shaper's philosophy embraced mass and momentum to power through inconsistencies that would stop lighter machines. Sarah examined the cutting action through her phone's slow-motion camera, watching how the high-speed steel tool bit deformed the metal ahead of the cutting edge. The material didn't shear cleanly like in her textbook diagrams. Instead, it compressed, buckled, then tore away in a process that looked more geological than mechanical. "That's not how cutting is supposed to work," she said, frowning at the footage. Tommy smiled. "That's exactly how cutting works when you're not afraid of the forces involved." He explained that modern machining doctrine had evolved around spindle-based tools, mills, drills, boring bars, all rotating components sensitive to imbalanced loads and deflection. Engineers designed those systems to minimize cutting forces through speed, shallow depths, and constant engagement angles. The entire CNC philosophy centered on keeping everything light, fast, and controlled. Shapers represented the opposite extreme: maximum force, minimum speed, intermittent engagement that would destroy a rotating tool through vibration and chatter. But single-point tools didn't vibrate. They plowed. The ram's mass absorbed shock loads that would rattle a milling machine apart. When the tool hit a hard spot in the forging, the shaper barely noticed. 7 tons of moving iron simply pushed through the resistance with mechanical indifference. The interrupted cuts that terrified CNC programmers, where tools entered and exited material repeatedly, posed no challenge to shaper operation. Each time the tool bit engaged the work, it simply compressed the material until shear stress exceeded the metal's strength. No spindle to stall, no servo motors to strain, no sophisticated control algorithms required. Just leverage, momentum, and mass arranged to make straight surfaces through brute mechanical advantage that made modern efficiency experts uncomfortable because it couldn't be optimized through software. The shaper started disappearing in the 1980s when manufacturing consultants armed with spreadsheets calculated cycle times and floor space costs. A 24-foot Cincinnati shaper occupied 600 square feet and produced 1 part at a time at speeds measured in feet per minute. A modern CNC machining center fit in 150 square feet, ran lights out overnight, and processed parts measured in pieces per hour. The mathematics seemed irrefutable. Even if the CNC needed multiple setups and tool changes, Its cumulative productivity exceeded the shaper's single-pass capability. Corporate acquisition specialists from Japan and Germany toured American machine shops in those years, cataloging equipment for modernization initiatives. They saw the shapers as evidence of industrial decline, massive monuments to outdated thinking that should be replaced with flexible manufacturing cells and just-in-time production philosophies. Insurance companies raised rates on shops operating equipment from the 1950s, citing safety concerns about exposed mechanisms and lack of modern guarding. OSHA inspectors issued citations for machines whose designs predated federal safety regulations. The last major shaper manufacturer, Rockford Machine Tool Company, closed its production lines in 1989. Their final catalog showed models ranging from 4-inch stroke bench shapers to massive 48-foot planer-type machines capable of surfacing entire locomotive frames. Orders had declined for a decade as shops invested in CNC technology that promised lower labor costs and higher precision. When Rockford's doors closed, replacement parts for thousands of installed machines became sourced through equipment dealers buying up inventory at bankruptcy auctions. Yet certain operations stubbornly resisted the transition. Naval shipyards discovered that modern machining centers couldn't handle the interrupted cuts and material inconsistencies of salvaged armor plate. Heavy equipment rebuilders found that 5-axis CNC programming for simple flat surfaces cost more in engineering time than the machining operation was worth. Tool and die shops kept their shapers for operations where a single roughing pass saved hours of CNC cutter path optimization. The younger generation of machinists never learned to operate them. Trade schools removed shapers from their curricula in favor of CNC programming courses that promised better employment prospects. Technical colleges sold their machines for scrap weight to make room for modern equipment that could attract student enrollment. Within 20 years, operational knowledge about shapers became concentrated among machinists approaching retirement, men who had learned the craft when American manufacturing still believed in training workers for 40-year careers. Tommy watched his shaper complete another pass, removing metal with the same unhurried efficiency it had demonstrated since. Eisenhower was president. Management had approved a maintenance budget that covered oil changes and occasional bearing replacement, but no investment in the machine's future. When he retired next year, the shaper would likely follow him into obsolescence. Not because it couldn't perform its function, but because nobody younger understood what that function was worth. Sarah finished her simulation and printed the cost breakdown. The CNC approach to machining the press frame totaled 47 hours of machine time, 12 tool changes requiring $340 in carbide inserts, and 16 hours of programming and setup. Labor costs at $75 per hour, consumables, and machine time at $120 per hour brought the total to $7,580. Her presentation to management would emphasize the precision, tolerances within 0.02 inches, surface finish suitable for immediate assembly, minimal secondary operations required. Tommy's approach told a different story that spreadsheets missed. The shaper's operating cost was $45 per hour, including power and Tommy's labor. The forging required 8 hours of cutting time to remove all 12 inches of material at 0.100 per pass. One high-speed steel tool bit cost $12 and would handle the complete job with periodic grinding. Total cost, $372. But the real savings lived in what didn't appear on any accounting report. When Sarah's third carbide insert shattered against an unexpected hard spot in the forging, the CNC went idle for 2 hours while she adjusted the tool path and ordered replacement inserts expedited from the tool crib. The interrupted cut strategy that looked efficient in simulation stumbled against reality. Each time the tool retracted and repositioned, thermal cycling shocked the carbide. Material that had looked uniform to engineering held pockets of hardness where carbon had concentrated during the forging process. The shaper encountered the same hard spots and simply powered through them. When the tool dulled, Tommy touched it up on the bench grinder. Without stopping the machine, the cutting action itself was self-clearing. Chips fell away from the reciprocating motion instead of packing into blind holes like they did during CNC milling. No coolant required because the interrupted cutting stroke allowed heat dissipation between passes. No elaborate chip management system needed because gravity handled evacuation. but the economic argument that management understood focused on throughput and utilization metrics. The CNC could theoretically run 24 hours per day with minimal supervision. The shaper required a skilled operator present during cutting operations. In an era where labor costs dominated manufacturing economics, the choice seemed obvious. Automate everything, minimize human involvement, maximize machine utilization rates. What the spreadsheets never captured was opportunity cost. While Sarah's CNC nibbled away at the forging over 2 days, 3 other jobs waited in queue, work that the shaper could have completed in hours, freeing the CNC for operations that actually required its sophistication. The modern equipment sat idle during setup and programming, during tool changes and debugging, during the hours when engineers optimized code to squeeze out marginal improvements. The shaper simply cut metal whenever work appeared, requiring nothing more than Tommy's experience to position the part and set the stroke. James Morrison had designed shapers for Rockford Machine Tool Company from 1945 until the company closed. In his Cincinnati retirement home, surrounded by engineering drawings and company photographs, he explained principles that contemporary engineers had forgotten. "We built for the worst case," he said, pulling out a cross-section drawing of a ram assembly. "Assume the casting has hard spots. Assume the operator will take too heavy a cut. Assume the work will shift in the clamps. Then design the machine to handle all of that without complaint." The ram's dovetail ways, hand-scraped too, match across 24 feet of travel, distributed forces through contact patches that spanned hundreds of square inches. When cutting loads tried to lift the ram, the geometry fought back through wedging action that increased contact pressure. No ball screws to backlash, no linear guides to bind. Just iron sliding on iron with oil films thick enough to float a bearing pressure of 40 pounds per square inch. Morrison's generation had designed these machines before computer-aided engineering existed. They calculated deflection using slide rules and strength of materials formulas from textbooks written before World War I. But they understood something that FEA software couldn't model, that mass and simplicity created reliability that complexity couldn't match. A shaper had perhaps 50 moving parts. A modern CNC machining center contained thousands of components, each one a potential failure point that could stop production. "The servo motors on those new machines," Morrison continued, shaking his head, "they're brilliant engineering, precise, responsive, programmable, but they burn out, the electronics fail, the feedback encoders drift. Our machines used a motor, a gearbox, and a Scotch yoke to convert rotation into reciprocation. Simple mechanics that a millwright could repair with basic tools." He showed photographs of Rockford's assembly floor where craftsmen scraped ways and assembled machines that would outlive the men building them. Each shaper received acceptance testing that verified cutting performance, not just dimensional accuracy. The test involved taking a cut through a hardened test bar with deliberately inconsistent material properties. If the machine completed the cut without stalling or chattering, it passed. No computer simulation, no statistical process control, just empirical verification that the design could handle real-world conditions. "We knew these machines would become obsolete," Morrison admitted. "Not because they wore out, but because manufacturing would change, smaller parts, tighter tolerances, complex geometries. The world moved toward precision and away from power. But there's still work that needs power. Heavy forgings, large castings, salvage materials. That work didn't disappear. We just stopped building machines designed to handle it and convinced ourselves that CNC could do everything better if we threw enough computing power at the problem." The press frame job finished on schedule. Sarah's CNC delivered a part within specification after 47 hours of cutting time, 12 tool changes, and extensive chip management. Tommy's shaper completed identical work in 8 hours with 1 tool bit and minimal supervision. Management reviewed both approaches and approved purchase of a second CNC machining center, noting that automation represented the future of competitive manufacturing. Tommy didn't argue. He understood the forces reshaping American industry: labor costs, global competition, the relentless pressure to reduce unit costs through higher productivity. The shaper's economics only made sense for specific applications, and those applications were disappearing as engineering departments designed around available equipment rather than optimal processes. But walking through the shop at night, after the CNCs had completed their programs and entered idle mode, he noticed something the efficiency reports missed. The machine sat dark and silent, waiting for morning shift programmers to load new jobs. The shaper could have run those hours, cutting metal with the same mechanical reliability it had demonstrated for 67 years. No software to crash, no network connection required, no security updates needed. Just a motor, a ram, and a tool bit ready to remove material whenever work appeared. The contradiction lived in what manufacturing had gained and what it had sacrificed. Modern equipment delivered precision that would have seemed impossible in 1958. 5-axis simultaneous contouring, adaptive control systems, tool life management, capabilities that opened entire categories of work that manual machines couldn't approach. But that sophistication came with fragility. Electronic obsolescence, software compatibility issues, specialized knowledge requirements that made every machine a unique puzzle. The shapers had embodied different values: mass over speed, simplicity over sophistication, repairability over efficiency. They were designed when American manufacturing believed that industrial equipment represented permanent infrastructure rather than depreciating assets. When craftsmen could restore worn machines to better-than-new condition through hand-scraping and mechanical rebuild. When the accumulated knowledge of operating these machines passed from generation to generation through apprenticeship rather than classroom training. Now that knowledge lived in the hands of men approaching retirement, operating machines that management viewed as obsolete but couldn't quite justify replacing. Because sometimes, not often but sometimes, a job appeared that needed what only these giants could deliver. Single-pass cutting power that made complex CNC programming unnecessary. The ability to handle material inconsistencies that shattered carbide tooling. Simple, brutal efficiency that measured productivity in cubic inches of metal removed rather than sophisticated tool paths executed. The shaper would outlast Tommy's retirement, probably outlast the building that housed it, definitely outlast the CNC machines that management considered its replacement. But could 21st century manufacturing afford to remember what 20th century engineers understood about the relationship between mass, momentum, and metal removal, or had we optimized ourselves into forgetting why we made the dinosaurs extinct in the first place?